Well, good evening, everybody, and welcome. My name is Dr. Eddie Lang. I'm the department head for emergency medicine here in Calgary, also a member of the board, and together with Rabbi Osachi and Jennifer Hatfield, who is the Associate Dean for Community Engagement at the Cummings School of Medicine, we are pleased to bring you tonight's edition of Tzed Talks, or Tzed Med Talks, which is now the second in a series that we've been having a lot of fun putting together. So you are in for a treat tonight. I'm going to be your moderator, introduce the speaker, and then do some moderation for the question and answer. But we are very excited about tonight's topic. It's about genetic testing and DNA, and you're going to hear about some amazing frontier developments in science and medicine and genetics. Robert, did you have a few things that you want to say? No, you're good. Okay. So it is my pleasure to introduce our speaker for tonight. Looked long and hard to find, but we are really thrilled to have such a high-level speaker here in Calgary. Dr. Anil Khan is joining us. He is an associate professor in the Department of Medical Genetics at the Cummings School of Medicine, also a very prolific researcher with the Alberta Children's Hospital Research Institute with multiple studies and papers on fascinating, rare, metabolic and genetic diseases involving bone health and other things, and is a world expert in some of these areas, including what you'll hear about tonight, which is the rare genetic diseases that affects the Jewish population. So without further ado, I will invite Dr. Khan up to the stage and invite you all to a fantastic presentation.
Thank you. So, mic is on. Thank you very much. And thank you, Dr. Lang and Rabbi, and thank you all for the warm invitation here today. I have a talk to give, but you could ask questions anytime, and I'm happy to shift topics and entertain any detail that you want me to for any reason. So I'm going to see if we can maybe dim the lights that are on the screen. It might be easier to see, and then we'll try not to put everybody in the dark. So, DNA. Who's heard about DNA? Anybody heard about DNA? Show of hands. Actually, the majority of people. So DNA is the genetic information we inherit from our parents. And it controls all sorts of different parts about how our body is going to develop, how tall you're going to be, what's your hair color, how big of a liver you're going to get, how well you might deal with medications that you get treated with or other agents in the environment. And of course, we have two sets of parents, so we get one set from our father, one set from our mother. So that DNA in us exists in pairs. And we're going to go through a journey today about what having DNA means. Kind of means that you're human and you're an organism in the very basic sense. And what it means when things don't go quite so right and you get different diseases and who's at risk for these diseases. So these are my disclosures, which means it's money that I got from various places. And what I always say when I show this slide is you can also be on this slide. All I need is a check from you at the end of the meeting, and I'm happy to put your name on there. And there are two things, of course, as part of our requirement from the university that we need to mention if there's a chance they'll be in the talk, is that I have a patent on a testing method for cell-free DNA combined with the university and for a gene therapy treatment that we'll talk about. And so these are the wordy objectives of the talk, but I think those are a requirement just to place them, and we can just move forward to this whole DNA bit. Now, most of you heard about DNA. Have you heard about genes? Now, not the denims that you get from the store on sale, but genes. How many people have heard about genes? So genes are basically regions of DNA that organize things. You can think of a gene as a book, and the DNA is the letters and the words. So if you want to read a story about something, you're going to pick up the book. That's the gene. And we're going to go through this short history of DNA, which was featured this month on the University of Calgary Medicine magazine. And what they're showing there is a picture of what DNA looks like. It's this helix. It's basically a ladder that's been twisted a little bit and coiled up inside your body. And you have about 1 trillion cells. So if you think about it, each of those cells has 2 sets of DNA, 1 set from each parent. So all that coiling is needed to package that DNA to start things off. And when we all started off as an egg cell from our mothers and a sperm cell from our fathers, that started off with 1 set of DNA, and it has to get copied. So if an adult has 1 trillion cells, that means that photocopier had to make 1 trillion copies. And things can go wrong sometimes. Maybe there's something running in the family and we get a gene that's not working that can cause disease. That's one way somebody can get a genetic disorder. The other way this can happen is when you go to make the 1 trillion copies, early on, you might stick your finger on the copy machine and get a little smudge, and now every copy that's going to come out is going to have a smudge, and we'll talk about how that can affect us. So that's kind of how DNA, either that we inherit from our parents or DNA going through changes in our bodies, can lead to different diseases. So sometimes, if you go back to that book analogy and you have a word, sometimes if the change is very minor, you can still be healthy, but you might have, maybe you're not going to be an Olympic athlete, or maybe you're not going to be the best swimmer, but you'll go through life just fine. Minor changes. Major changes, though, can sometimes cause disease. Sometimes a baby can be born without an arm. Sometimes a baby can be born without a heart, or the heart's not working properly, because that DNA contained the instructions on how that heart should form. So we know major changes can cause disease. Now, looking for those changes is like looking for a needle in a haystack. It's literally like going down to the library. If I sent you down to the library and I said, there's a spelling mistake somewhere in a word, go find it. And your traditional way of doing that would be to read every word in that book and have a dictionary that you can match it to say, oh yeah, that's a spelling mistake. Very tedious to do. But what's happened over time is the technologies to do that reading. So now imagine if it wasn't just you said, well, okay, suppose you were in part of a basketball team, and you said, that's fine. All my buddies are going to go there, and we're all going to read through those books. That's going to work a little faster. And so what's happened with computing technology is we've seen this big escalation in how fast we can do the reading of the DNA. And the details in the slide are not important, but look at the scale. From 1980, we've gone from a factor of 10 to, I don't know how many millions zeros are in there. There's 9 zeros, right? In just a matter of 20 years. So a huge scale up of technology in terms of how fast we can read the DNA. So when we get a child is born with a certain type of disease and we're wondering, this looks like probably something's not working in the genes, our ability to now read through that DNA has increased considerably. And what kind of scale are we looking at? Here's an analogy that many people use, is suppose you had to evacuate the planet. Some asteroid was coming and somebody said, okay, everybody's got to get off. I'm not sure where we'd go to, but you board a plane and go off. And suppose, with the old technology, you could put one person on a plane. And you can imagine the scale, how long that would take to evacuate everybody. With this new technology, your plane would transport everybody sitting on every flight anywhere in the world at one time. So, times 1.5. So that's the scale at how fast you can read through that library to see if you can find spelling error. And that's happened through this technology, which is called, it's got a big long word, it's called next generation sequencing. I don't know what they're going to call it in the next generation after that, but right now it's called next generation sequencing. So this is a machine, there's different companies that make the machines, that's basically the size of a big printer. And it can read through DNA code like that in about a few hours, it will read your entire DNA code. So you can imagine what's happened with cell phones and computers, right? You used to work on these big computers and you had these floppy disks, and now your cell phone can hold more memory than every floppy disk you ever used in your entire life combined. And these DNA sequencers are going to be getting smaller and smaller and faster and faster. And there is even technology right now that can scale it to the size of a USB thumb drive. So imagine having that level of technology to do sequencing and to look for things. Now, there's about 3 million Canadians that might have a major change in the DNA and get a rare disease. That's the group of things that I do on a daily basis. Somebody comes in with a liver problem or a muscle problem or a neurological problem. They're saying, well, there's got to be something in the DNA that's causing this. 3 million Canadians. What this technology does is, you can imagine, if I have to look for that needle in a haystack, it's going to make it a lot faster to find one. It used to be before you'd come in, this was not even that long ago, and I would test for one gene at a time. That analogy of one passenger on one plane. And as of this year, the province started a program with this next generation sequencer. We can actually do the analogy of just testing everybody on every flight, everywhere in the world simultaneously. So that's happened already this year. But 3 million Canadians will be affected by a rare disease. But every Canadian has DNA. And every Canadian will probably have some shift in the DNA sequence in some region that might make it so that a certain antibiotic may not work as efficiently. Or you might metabolize your coffee differently, and the risks that are associated with taking different foods and fats may be handled differently. We know a lot less about those changes because we would need to do sequencing in a whole bunch of people and find out all those different variations to find out what that really means for an individual person. So we have to look at large populations. And that type of work is going on in the UK, for example. They have DNA sequences on 500,000 people in the database, and now they're starting to do the analytics on how that can influence certain diseases, diabetes, heart disease, cancer, and so on. So how are these changes in DNA going to affect you? So we talked about the spelling analogy, and it kind of can work like this. So suppose there's an instruction, a DNA code somewhere, and I don't think we found this one, but it probably exists. Make 5 fingers, right? Now some people are born with 6 fingers, so we know there's a change in a code somewhere and it made an extra finger. We just haven't found which code it is. And you make one spelling mistake and you get this result. Make fire fingers. That kind of highlights some of the changes. Now, fire is not a number like 5 was, but that's the code. That's the instruction that you have. You're born and your instruction says make fire fingers. So the machinery of your body is going to say, well, we got to do something with this. I don't know. Do we make 6 fingers? Is that what it's saying? Or do we still think it's 5? Or do we forget about making fingers? It's too confusing. And any one of those things can happen when you get a change like this. The term biologists use to describe the change sometimes is mutation. That's where they get that X-Men movie from, right? Mutations that give you special powers. That can happen sometimes. You look at really intelligent people like Albert Einstein, for example. And probably the DNA that he inherited caused the pathways in his brain to form a certain way that they can process things a lot faster than I can. I can't do very much physics at all, let alone the equations. I can't understand his equations, and he came up with them. So those instructions then, if there are changes in those instructions, they can either be very subtle and make it difficult for the body to know what to do with them, or they can be pretty significant. And we'll come back to this analogy later. But that's really what your DNA is. It's just a bunch of code. Oh, okay, so this is a liver here, and you're going to put it on the right side. Here's a heart. It's going to have 4 parts to it. You've got to make these blood vessels. Just instructions. And that's what your body does all the time. It just goes through, reads the instructions, and said, oh, okay, we got to make this, or we got to break down this. So this is a little hard to see, but it just looks at the world population, and I'll read it out for you here. So, of course, somewhere it had to be a very small number, 1,000. This scale here, we got 10,000 years before the Common Era here, and we've got last ice age, 5 million people. I don't know who did the census. It must have been really cold, but that's the estimate, about 5 million people. So now we've got 7 billion and change, and it keeps going up. But you see really this big exponential rise is happening around here, and if you can make out the graph, there's sort of the time of the Roman Empire, and that's also the big expansion we see in the Jewish population also comes after this Roman Empire phase. And you can imagine then you have a community of people. And suppose in that community of people, there's a few people that might have a certain genetic predisposition to something, and they're going to have offspring, and they're going to marry other people's offspring, and so on and so forth. And if that community was staying together, that's going to be very different than mixing in with the other 7 billion, how those genes mix in. So we'll talk a little bit about that. So here we've got an example here. So suppose we've got a small community, and we've got a grandfather had kids, and they had kids, and so on, and these red people represent some genetic variant that's in the population. And the chance in a very large population, so the black people here, the black colored figures are the ones that don't have that gene, the chance for the folks with the red to meet is probably very small, because of course I didn't want to draw 7 billion people here, but you can imagine 7 billion people on the slide. Their chance of meeting is very small. Right? If you do the math, suppose you said 1 in 7 billion times 1 in 7 billion, that's a very low chance that something is going to happen at one of those genetic changes. But now you're dealing with a small population. Suppose you're dealing with the Jewish population. There's probably max 15 million Jews, top estimate, rounded up. If somebody's got a better number, then go ahead and say it, and we can revise it, in the world. 7 billion other people. So now your chance, if you're going to marry somebody within the community, that you're going to run into somebody else that might have that gene goes up. And we'll have some diagrams to show how that gets transmitted. So here we have that 5 and fire analogy. We have these two people. They got married. They say they want to have kids. And here's their picture of their little DNA. And one of them has got a change in the DNA. Now, remember we said we have two parents. We have two copies of everything. And the reason for that is if one copy is changed, there's a second copy there as a backup. And there's a lot of conditions in which the backup, not having two abnormal copies, means you're healthy. You might carry something. Each of us carries 12 to 16 lethal genetic mutations. Each of us. There is no human that doesn't have that. So having one of those is fine. If you got the second copy, you're healthy. Nothing's going to happen to you. You're what we call a carrier. You don't look abnormal either, right? There's no way to tell. Look around the room. Can you tell anybody's a carrier for which 12 or 16 of those genetic mutations? I can't. So the carriers look fine, and they're healthy. But if they were to come together and have offspring, they're going to send one of these two pieces of DNA down to the offspring. And so we get a pattern where you could get this piece here from this fella, and from the mother, this piece. No mutations, right? Not in that combination. Looks like they're fine. And you have another scenario where this can happen. This should actually come to here. That's another carrier. Not a big deal. Let's say it's cystic fibrosis. Carrier for cystic fibrosis, they're never going to get cystic fibrosis. And same combination here. Again, you got another carrier. It's just that the other gene came from somebody else. And finally, you have this scenario. So which one of these scenarios do you think produces the disease? This one right here. So now you have, by chance, because none of us decide which one of our genes we're going to pass on, right? That's kind of happening automatically and stuff like that. So you don't decide, oh, hang on, son, I'm not going to give you this gene. It's just going to happen by chance. So one out of these 4 possibilities that if it's a carrier couple they're going to have offspring that just by chance got 2 of those genes together. So 4 possibilities, and usually what we say then is that's about a 1 in 4 or 25% chance. So if the parents are carriers of a rare disease, then there's a 25% chance that each of their offspring might get that disease. Now, it doesn't work like formula math. Each pregnancy has a 25% chance. So could you have 2 kids in a row that are fine? Sure. That's the opposite of this, 75, so 3 out of 4 times 3 out of 4, depending on how many kids you have. You just keep doing the math and multiplying, right? But, I met a family last week that moved here from Newfoundland. The mother and all 4 of her kids have a particular type of disease. So sometimes, mathematically, the odds might produce multiple kids in the same family. And in fact, there's nothing new about this. Picture's a little fuzzy because of the resolution, but I'll read it off to you. This is a website of the Jewish Genetic Disease Consortium. How many of you have run across this website? And so this lists the different disease groups, ones that are common to all Jewish people and ones that are common to Ashkenazi Jewish people. And this is just a snapshot of the page. When you scroll, it just keeps going on and on and on and on for a while. And this is to educate people, to inform people of things they may be at risk for if they're considering having offspring. And this is the website, and we can talk more about it. Like I said, you can stop me at any time. We can go into some parts in detail. So, now, I'm not going to list all those things. And every group has a list of things. That just happens to be for Jews. But if you looked at different folks around the world, you could find different things that were common in them. Why? Because, again, in some countries, you had a small group of people from which all the offspring took place. And if there was a mutation in a particular gene, then that's what's going to be prevalent. Now, you might ask where the mutation come from. That's a good question. Oftentimes, we don't know. When you're making copies of DNA, small bits and pieces of DNA, the machinery that does it is imperfect sometimes. Most of the time, it catches a mistake. That's why we have 2 strands of DNA, because it looks and it says, hey, wait a sec, that other copy doesn't have the same change, and there's a mechanism to go and fix it. But like not everything is perfect, so sometimes it misses that. So sometimes it happens because there's a reading error. Sometimes it can be something in the environment. We know if we're exposed to radiation, the number of mutations goes way up, right? So you look at the Chernobyl accident, for example, and in that area, you had a lot of different effects on different animals that, of course, didn't have a chance to run away. It could be chemicals in the environment. It could be other things that we don't understand fully that can produce those mutations. But once the mutation is there, right? So if you had a poster for tonight's talk, and you had a spelling mistake and you took it to the photocopier is not going to correct it. Maybe if the word processor corrected it, that was your last chance that your spell checker was going to do. But once it hits the photocopier, that's it. That mistake's going to be copied. So that's what's going to happen in the cell as well. So the number 1 is Gaucher disease. How many people have heard about Gaucher disease? So I know, how many people have heard about Tay-Sachs disease? So more people have heard about Tay-Sachs disease, but look at this. 3 times more common, if you're Ashkenazi Jewish, that you're a carrier for Gaucher disease. We can talk about what Gaucher disease is. How about cystic fibrosis, right? It's actually a little bit more common than Tay-Sachs disease. Now, cystic fibrosis is on the newborn screening panel in Alberta, which started around 2007. So if any of you have had a baby recently or have had grandkids recently, you'll notice that there was a little heel prick done on the baby and then a little card which had 4 blood spots that went up to Edmonton, and they screened for a number of different genetic diseases, and one of them is cystic fibrosis. Because if you catch it early, you may change the course of the disease. In fact, there was this interesting study out that showed cystic fibrosis. Back when I was a medical student, we learned that you're lucky if you get to teenagehood. You're never going to make it to 20 if you've got cystic fibrosis. Now we have people living in their 30s. And in fact, in Canada, where we haven't had as many expensive drugs for cystic fibrosis compared to, let's say, the United States, you actually, on average, if you have cystic fibrosis, you can live 10 years longer. So all those little advances, the early knowledge, the testing, the screening, have made a difference in those people's lives. Now, it could be in your life it didn't make a difference, but that's good. You're fortunate and you don't have one of these diseases. But for somebody with those diseases, all these advancements have made a major impact. In fact, 1 in 4 Ashkenazi Jews may be a carrier for a Jewish genetic disorder. So that goes back to those diagrams of the red images that I showed you and the population size. And if you are a carrier for a disorder and you know that you're, let's say, marrying into a population that has a higher carrier rate, maybe you want to find out if your partner is carrying that as well. Your other option is to just go find a random person out there, which you can do. It doesn't mean your chance is zero. That carrier, that's how 50% of the recessive disorders actually manifest, is random people having kids. Because you can't tell when you walk out in the general population if somebody's a carrier. Could be anybody. So your family history might put you at higher risk for certain diseases. That's what happens with these genetic conditions. And then when we look at the genome and we try to find all these diseases, I mean, needle in a haystack is not even an apt analogy. 3.5 billion letters of code. It's 80 encyclopedias. You're looking for one spelling mistake. Now keep in mind that each of you is different unless you have an identical twin in your DNA code from the person sitting next to you on 1% of these regions. 1%. So that's going to be at least 25 to 50,000 differences that you're going to get from this result, just because you tested, let's say, me versus you. But you're looking for one spelling mistake that caused the disease in that region. So that's a little tough. This is a genome map. It's a very dense genome map, but you got to find one pixel here. So you can imagine, without this next generation sequencing technology, this is a very daunting task, and it always used to be. And some people didn't get diagnosed. Now, if we found what that change was, knowing about your genes might tell us what to watch for and what to do. So who's heard the Angelina Jolie story? And what was her story? She found out that she has a gene that puts her at higher risk for breast cancer. Didn't mean she was going to get breast cancer, but it meant her risk was higher. And she made a decision to have a bilateral mastectomy. So now, that doesn't mean the consequences are going to be, oh, maybe you can take some vitamins and you can thwart this. The consequences may be quite dire in terms of what decisions to make. But that doesn't mean that those decisions aren't increasingly becoming available. And that's just one extreme example. And incidentally, if you're Ashkenazi Jewish, there is a higher carrier rate for those breast cancer genes. In fact, if you took somebody from the general population that had a family history of breast cancer, and you decided, well, no, you need these criteria before we test you, and you threw in that they're Ashkenazi Jewish, all of a sudden you got the criteria, right? So you have different flow charts if you're Ashkenazi Jewish and you're testing for breast cancer versus if you're not. So that information about family history, about heritage, can influence these medical decisions and what to do. And some of it could be as simple as saying, you know what, mastectomies are going to start earlier if you want to affect your chance of having breast cancer compared to somebody who didn't have the gene. We'll do surveillance earlier. If we find a lump, we'll tend to biopsy a little earlier. All those different decisions can go into play depending on the background. Now, of course, I was asked to talk about things common in Ashkenazi Jews. That doesn't mean it's the only population that's at higher risk for different things. If I was giving this talk somewhere else, I'd pick the different things that were in their category. So it varies. So, this whole business of looking at this DNA and looking at genes is called genomics. And genomics is at the heart of trying to find a rare disease. And this graph may be hard to see, but there's a lot of diseases that are so rare. In some cases, yesterday I saw 2 kids. One of them, she's only the 2nd case in the world with that disease. And we found it through this sequencing mechanism. We didn't know what the heck it was. When we found it, we were like, I don't know, what is that thing? And we did a couple of years of work to show that it actually caused the problem. But when you add up in each of those individual rare diseases, that's where you get these numbers. 7,000 rare diseases. Like I said, 3 million people in Canada, 350 million around the world. So it adds up. And the trend now is shifting towards understanding the genetics of the disease, understanding how it affects the chemistry of the body, and then engineering a drug. So it used to be Things like digoxin, which we use to treat certain types of heart failure, that's a compound made in a plant. A lot of the chemotherapies are compounds made in plants, and that's how things were looked at before. But now what's happening is, by understanding the gene and the effect of the gene, the compound is being engineered to go and target that area. So it's not a random find of a compound anymore. It's being shifted towards engineered compounds, and that's what's changing. Average doctor will see 40,000 patients in their lifetime. And the worldwide estimate of a rare disease is 9.19%. That means if you're a doctor in a lifetime, you're going to see 3,700 people with a rare disease. So if you learned in medical school not to pay attention to this, they're under your nose all the time. You've just been missing them because the number of rare diseases is going up. So how is this going to affect you? You're like, well, I'm 75. Doesn't look like I have a rare disease. Well, that's good. You don't. But there are probably other ways it could affect you. Now, yes, in the pediatric side at the Children's Hospital, this is how it affects us. We're looking for a rare disease. So I got a call just before I came here, baby who's on a ventilator and something abnormal on the MRI. They're like, I think it's something metabolic. I'm like, I have no idea what it is, but maybe I'll try to find out tomorrow. But I'm starting from scratch. You could do carrier testing to screen a couple for a rare disease, like Tay-Sachs disease. So when I was in Toronto, working with the Jewish community, community centers and synagogues, they would have an education program about Tay-Sachs, and if a couple wanted to, they could send their sample over to the hospital for sick children and get screened to see if they're carriers. Because we said if both members of the couple are carriers, there's a 25% risk they're going to have a child with that rare disease. I haven't seen anything like that in Calgary, and we can talk about whether there's sufficient interest to look for it, or people can come individually and they can get screened. I don't make any dollars off that, so that's all over in the hospital. But that's something that can inform the community. The screening programs in places like New York City in the Jewish community are quite large. And in some cases, if a couple is betrothed, they might go through a carrier test to find out if they have a rare genetic disease before things are finalized. So there's a large amount of awareness of this in different communities. And I guess tonight's just one opportunity for me to talk about it with you guys. It's also important in treating certain forms of cancer. There are certain types of cancer, and all cancer at its heart is actually genetic. There's a mutation somewhere in a cell that's telling it to grow abnormally and to fight off all the chemotherapy that we're throwing at it. But what we've learned is if we understand what the mutation is that started the cancer, we may target certain drugs to it. So for breast cancer, for example, you can do genetic testing of the cancer cells themselves, and you can target certain drugs towards that breast cancer to get a better rate. It does work. You can also tailor treatments, not just to the group, but to you. Now, there used to be, when we looked at studies in medicine, we'd say, okay, we're going to take 5,000 people, and we're going to give them this blood pressure drug. Because, of course, all those 5,000 people are the same, right? They're going to respond to the drug in exactly the same way. They had the same starting blood pressure. But okay, 5,000 people here, 5,000 people on placebo. We'll see what the effect is. They're not the same person. They've got a different genetic code, each individual. They eat different things. They eat different amounts of salt. They exercise at different rates. So what's happening now is, with this genetic information, we're looking at tailoring, either studying these drugs or certain treatments, so that they're directed towards the individual and certain risk factors that they have, including genetic risk factors, and not just that individual as being part of a big group, like men over 45 years of age, because all men over 45 years of age do the same things. Well, it looks like some of them do if you've been watching the news recently, but we'll stay out of that. So here's an example, a real-life example. Finding a rare diagnosis. So a 6-month-old girl I was asked to see, she kept having low blood sugars. So low blood sugars, if they're really low, they'll kill you. So it was a pretty serious problem. Nobody knew what was causing this. She had multiple admissions to hospital, multiple tests done. They even did this test, which I don't like doing anymore, where you don't feed the child for a while and you wait to see how long you can last before the blood sugar falls, and you keep testing blood every couple of hours. And I'm like, geez, that's cruel. Who invented that? Okay, I don't do that anymore. No answer. So I said to the parents, I said, look, I'm not as smart as I look, and I know you came here for an answer. I know there's a gene somewhere that's not working, and I can look for it using the old-fashioned method, one passenger on a plane. And if I was really smart, I would guess it right away, but I'm not. And we could use that approach, and technically, if you look at all the genes that cause low blood sugar, we could be doing this for about 170 years. Or, if you want, when this test was not available through the public purse at that time, you can pay $5,000 US and I'll send it to a lab, and let's see if we get an answer. So they hemmed and hawed, but their daughter's health is at stake. So they said, fine, here's the Visa card, or MasterCard, I forget what it was. Paid the money, and boom, we got an answer. It was a protein that's coded for DNA that moves glucose from outside the cell to inside the cell, a glucose transporter, we call it. That was the definitive answer. And the treatment was that she should go on a diet that has a lower amount of protein, and we can use a drug, a common drug that we use called diazoxide to control blood sugars. 2 simple treatments. They didn't cost very much. Now it's 3 years, no more low blood sugars. Right? Very simple answer. Sometimes they turn into very significant things like, uh-oh, we got to transplant you, or uh-oh, we got to do this thing. But this was a very simple one with a simple answer. Now, what I don't want to do is stand here and say, if you do all this next generation sequencing, you find out the secret to all your genes is going to solve all your health problems. Because there's still things that we do which are more significant sometimes than the genes. I was saying to Dr. Lang, finding out if you have cystic fibrosis is probably not going to prevent a car accident or dying because you didn't wear your seatbelt. Like, those are, I guess you could argue there's some genetic basis to that too, because a certain lack of intelligence if you're not wearing your seatbelt when you should. But tobacco smoking is still the #1 killer in the world, right? So look at the smoke business here. You got tobacco smoke, you've got indoor smoke, ambient particle pollution, and secondhand smoke. So you took smoke all together, that's like more than actually all the other stuff sort of combined almost, right? So what I tell my patients, my adult patients, I end up seeing a lot of adults that have rare diseases. I say, I could put you on a drug that costs $250,000 a year, but it's not going to take away the effect of you smoking. So first you got to stop smoking. So we have to put the genetics in perspective of these other factors as well when we look at health and improving outcomes. And this study looked at the component of genetics with these other factors, and it found that for heart disease, about 20% of your risks with heart disease, your outcomes, could actually be influenced by genetics. Almost 10% for lung cancer, so on and so forth. But this is based on what we know today. What we find, though, is that these red bars keep increasing as time goes on. So suppose somebody's having a heart attack. Well, their clotting, their natural tendency to clot, their ability of their heart to resist lack of oxygen, their ability of their blood vessels to recover and their brain to recover that may be affected by their genetics is all going to go into programming what their outcome is going to be. And it can vary. You look at villains in movies, for example. They never die until the end, and that's when the police come in and they capture them. But there are some people you look at and you're like, they're so resistant to infection, to disease. You have people living longer and longer in the world today. It's not really because our genes have changed that much. It's because our environment has changed. We have less rates of infection. We have improvements in health and so forth. But there is a tendency for longevity to cluster in families. So those families where you have your people living over 100 years of age, there is a genetic factor that allows them to go past 100 if they took care of themselves. So you can't really get rid of your genes, and you can't really escape their effects. So this takes us into this concept now. We've talked about environmental things and tobacco smoke and alcohol intake and so forth. We've talked about genes, and now we're going to go into this fancy term called precision medicine. So the university uses this term a lot, and I figured, well, okay, they didn't tell me what to say, but I figured maybe I'll talk about it, because then when you hear this term in Calgary a lot, you're going to be like, well, what does that mean? And that guy never mentioned anything about it. Okay, so here's an example of precision medicine. So you got these superheroes, and you've got a villain. The villain is going to use a generic method with which to fight these. Brute force, whatever it is, maybe some tricks. Now, but you tell the villain that one of them is very susceptible to the effects of kryptonite. Does everybody know what I'm talking about? Who's susceptible to kryptonite? Superman, right? It weakens him entirely. If the villain has that bit of information, then all of a sudden he can target at least one person in this group and defeat them. That's precision medicine. So you're not looking at the whole group. You're trying to pick out different things and different individuals that may allow you to target your different treatment. We can go into and talk about what those treatments are, but I thought this analogy was, I don't know, kind of came to my mind when I was making the slides. So we've got precision medicine, and we've got the DNA information, plus the things that you do in life, and all of that is going to feed into this new model of trying to deal with disease, deal with your health, and so on and so forth. And that's what, when you hear that term, that's what it's going to affect. So, how is this going to work? You know, right now, if you wanted one of these DNA tests with this next generation sequencer, you're going to be going to a specialist, most likely. There's myself and about, I guess, 9 or 10 other people in the city, which means you might be waiting for a while. So it's new technology. Actually, none of us were trained on this technology. We're all learning this because, you know, I guess we've gotten far enough in our careers with this new technology. We're like, hey, what's that new stuff? We better learn about this. But probably not too far in the future, the time will come when your doctor might send, your family doctor might send the test themselves, or the pediatrician, or whoever you're seeing. Maybe an emergency medicine doctors, you never know. And a time will probably come where you might send the DNA yourself. I mean, this already exists. It's, you know, you can check your ancestry, for example. What are you doing? You're sending your DNA. It's actually going through the same process. It's just that they aren't regulated to report different disease genes to you. But it's not because they can't find them. In fact, they probably have them in their database because the way the sequencing technology works, you can't pick and choose individual genes to sequence. You sequence entire regions. You find all sorts of stuff. How do you know what to look for? How do you know what it means when you get a result? If you get a result, like Angelina Jolie did, that said you have a gene for breast cancer, all of a sudden you're going to think, okay, I'm going to die of breast cancer, and I'm going to put my life in order. Maybe it only increased your risk 10%. Maybe you didn't have a lump. Maybe it wasn't going to kill you at all. So there needs to be some way to process that information so that the person that's getting that information knows really what impact it's going to have on them and where to put things in perspective. So, of course, in this day and age, for example, we have patients that come to us, they're like, Doc, I know I got this disease. And I'm pretty sure of it. I looked it on the internet. And I'm like, I don't think you got that. They're like, no, I'm pretty sure I have it. I'm like, well, every person that had that disease died at 5 years of age, and you're 45, so I'm pretty sure you don't have it. Well, it's got to be that. You're wrong. Imagine now having the DNA technology, and you have a sequencing result, and it's showing something, some type of cancer or some type of other thing that doesn't look well. So we're going to have to figure out how we're going to deal with that when the public has access to that information. And then, you know, sort of tapering things off. This thing, I got a new car recently, and then when I was getting it, the salesperson said, "Oh, it's got this fascinating auto stop technology." And I'm like, "What?" I'm like, "I don't want that option. Take that out." She's like, "No, all of them come with that." I'm like, "How can you not take that out?" They're like, "All of these cars come with auto start." So what happens now? If I'm using it, it stops when there's a red light, because that's what it's supposed to do. And it's still a funny feeling, because then you lift your foot off the gas and it starts again. So if I use it, I have to engage with it. If I don't want to use it, I have to hit this button every time I start the car to disengage it. So no matter what I do, I can't ignore this technology in my car. This is what's going to happen with this genetic information and exome sequencing. Whether you engage with it or don't engage with it, it's still going to be there. I don't know, like airport security, right? Which one of us really has something to take across that's going to do anything? But we're all going to get screened. the same way. So there's nothing you can do about that. How many bottles of water have been thrown out that way? And some of this stuff is not really in the future. It's here. So when did we do this? 2013, that's right. You know, we had there's severe liver disease. We get a lot of these cases in Alberta. And we decided, well, waiting for an organ transplant can take a long time. What if we injected liver cells that we got from organ donors into patients to give them a little bit of extra time until they could get a liver transplant? So here you see me injecting this syringe of cells to a baby who's very sick. And this is her this year. Father sent me a picture. He's like, she's starting school. We put the liver cells in. It controlled her ammonia level. Then she went to Toronto a year and a half later. She got a liver transplant. She's learning 2 languages. She's doing very well in school. Most of the time, this disease is lethal. If not lethal, it causes severe intellectual disability because of the metabolic effects. So there you go. We've done five patients so far putting liver stem cells in. Gene therapy. We talked about the genes and how they can cause disease. What if I told you we can put a correct version of the gene in? You'd think, well, I thought that was going to be the talk 5-10 years from now. No, we just did our second case 2 weeks ago. What we did was we took stem cells from the patient. We put a working copy of the gene in, and we put those cells back into the patient. They're the patient's own cells. Now they have a working copy of the gene. So this is a photo from earlier this year. And this man with a disease called Fabry disease, which is another lysosomal disorder, the same way that Gaucher disease is a lysosomal disorder. And the first gene therapy in the world for Fabry disease occurred right here in Calgary. So this is Dr. Jeff Medine, he's principal investigator, and I'm the local site investigator for this. So this is happening. It's happened now for adrenoleukodystrophy. There was a paper out in the New England Journal of Medicine. It's being looked at in Gaucher disease. It's going through different phases of trials. And it's being looked at for Tay-Sachs disease. My understanding is there's a trial starting in the United Kingdom for gene therapy for Tay-Sachs disease. It's already approved for certain types of immune deficiency in Europe, where the kids would die because they don't have an immune system, and they're being treated with this gene therapy.
So if you could do that, why can't you get rid of the stem cell? I mean, using stem cells, get rid of the gene that's causing this problem.
So the question is, why couldn't we use the stem cells to get rid of the gene? So the stem cells will go in there, and they'll make their own pool of cells, but they won't go in and fix the old cell's genes. Those genes are still causing a problem. And we have a trial, we're part of an international group where we're actually injecting the virus to go to the liver and then replace as many cells in the liver with the gene. So there's a stem cell approach and there's also the gene therapy approach. The only thing is it takes a long time to develop these. I mean, Dr. Medine worked for 20 years to develop this technology. And then he and I were chatting at some meeting and we're like, hey, let's do this. This is what doctors do in their spare time. And we said, okay, let's write a grant and do this. We wrote a grant and the CIHR approved the grant along with a consortium across the country. And we went forward and did this. So a little bit of a busy slide, but again, with anything, we have to temper the advances and the excitement with real things. So let's take a look at a common disease, diabetes, right? So if a drug lowered the risk of complications of diabetes by 2/3, the estimate is it would cost about $150,000 a year. That sounds like a lot of money. The most expensive drug I dose is $2.7 million a year. An incredible amount of money. I wish the prices could come down, but that's their cost. This effect with this new drug would be the same as diet and exercise. And in the last 50 years, the lifespan of the average diabetic has increased by 10 years with no knowledge of DNA. So as much as I'm here to plug DNA, sometimes, getting your brakes fixed in the car and putting a seatbelt on is better than getting an exome sequence as far as your life is concerned. So you still have to do those basic things. Take another example, drugs for rare diseases. So chloride channels have a problem in cystic fibrosis. There's a drug that works for only 5% of cases of cystic fibrosis at $300,000 a year. Not available in Canada yet. However, when you compare it to good old-fashioned chicken soup, plus ibuprofen, saline, which is salt water, and an antibiotic, that's the same net effect on mortality as that drug that costs $300,000 a year. So what we're going to be faced with as things come on board is expensive drugs for many of these rare diseases. Some of them are going to cost $1 million a year or more. And as a society, we need to have a discussion about what drugs are going to be funded by the public system and what the public system is prepared to do on its own. And then people like me have to look at this and say, well, gee whiz, is this sustainable? Maybe we got to come up with some other ideas to see if we can produce a sustainable effect that's affordable to a public health system. Those are all challenges that are coming up. So we still need to make sure precision medicine is evidence-based and is economically feasible. And finally, this is a survey done in 2011 looking at what patients really want from healthcare. And the top priorities, some of this makes sense, restoring health when you're ill. They all gave good responses. Timeliness, something the doctors, I guess, will need to take note of. Kindness, right? They just don't want their condition to be fixed. They don't want to feel lousy going through the process of getting it fixed. Hope and certainty. We haven't hit genetics and exome sequencing yet. Continuity, choice, and coordination. A private room. That's toughie. Okay. No out-of-pocket costs. That's going to be a toughie too. If you're an adult, you have to pay for the TV in your room. Otherwise, you're going to sit there. I don't know if any of you spent time in a hospital room, but if you don't have a TV in an adult hospital room, you're going to be listening to other people. It's no fun. I once walked into a room to see my patient. It's a ward room at Foothills with 6 beds. And a few of them looked at me and they're like, "You the doctor looking after that patient?" I'm like, "Yeah." "When the hell are you going to get rid of her?" I'm like, "Why?" And she was just on the phone and talking and saying things. I'm like, "Oh, that's not what I expected at rounds." No out-of-pocket costs, and they want the best medicine, right? And that's something, I guess, when we look at this list, there's many things here which we should be doing already every day. Kindness, hope, and certainty. But this is one we should also be doing. We shouldn't be giving you grade B medicine or grade C medicine. "Oh, try that and see how it works." Usually what we try to do, many people I know, including myself, what we try to do is at least tell you what the best way to treat this is. Maybe we can't access it. We don't know how to. Maybe it's not even available in Canada, but we want to give you, this is the best way to do this. This is what we have access to. And you know what? If you have to go somewhere else to get access to it, that's your choice. But at least we're not hiding that from you, because people want the best medicine. And so the last slide just indicates that at its very heart, in its chemical nature, DNA is just a sugar. So that old saying, "Sugar is sweet and so are you," is true, because our genetic code is made up of sugar, basically. So with that, I will end the talk and then entertain any questions you have.
Great. Thank you very much, Dr. Khan. A fascinating insight into what the future holds for us from a genetic perspective. I'm sure you've sparked a number of thoughts, and would be welcome any questions from the audience or any comments or experiences that you might want to share. I don't know if you remember Phil Donahue. I'm going to be Phil Donahue. I'm going to run around and carry the mic here. Yes.
Can you see the day when health insurance companies will enter into this picture, demanding testing before they issue certain insurance?
So, very good question about health insurance companies entering into this picture and so on and so forth. They're already in the picture. They're kind of like that auto start stop feature. Whether they want to or not, they're confronted with this. So many times if you already have a health insurance plan, they've built into that if it's an approved therapy, they're going to cover it. Sometimes they may be putting a cap on it, saying, well, we're going to give you whatever, $500,000 max in your life, and then you got to go find a cure. Sometimes they do things like that. But private insurance will fund certain therapies, sometimes to a certain extent, but most Canadians are in the public system. And so it still won't reach out to the majority. Now, as you know, there's a bill going through final readings in the Senate that will make it illegal in some ways for insurance companies to discriminate against you if you get diagnosed with a certain genetic condition. Like suppose you get found to have one of the genes that increases your risk for breast cancer, and the insurance company would say, we're not giving you insurance. They may not be allowed to do that anymore. How they're going to deal with it is not clear. So there is a bit of a debate and a battle going on how this is going to take place, but I think for many people who have a genetic condition, they welcome that type of legislation. Of course, the insurance companies don't.
The BRCA1 and 2 mutations have been known about for quite a long time. I understand there's also something called BRCA3. And my question is, in terms of breast cancer, are there other mutations beside BRCA1, 2, and 3? And will they also be on the same, probably on the same gene? Or do you think they will find mutations that cause breast cancer on other genes?
So it's turned out there actually was a paper that came out within the last...
Could you speak louder, please?
Oh, sure. Do we have... how's that? Is that easier? So there was a paper that came out in the last month that actually showed now a multitude of genes that affect breast cancer risk, and they're in different regions of the genome. So some of them are going to have a stronger effect than others. Now, when a paper like that comes out, what that means is a research lab somewhere or a small number of labs have looked at that. It takes time for that to trickle down into the local lab to add it on to their panel, let's say. So it's not immediately available on those panels, but over time, the local labs will look at it and then decide if more studies have come out that support that evidence, whether to add them on the panel.
And also, the Ashkenazi Jewish population has a fairly high risk of having one of the BRCA mutations. What about Dutch people?
Dutch people. So I don't do that much cancer anymore, but I don't remember from the days when I did that there was a higher rate in Dutch people or people from the Netherlands. But there were studies that were showing certain other populations, like the one I come from, South Asians, that the risk may be as high as in Ashkenazi Jewish people. It just hasn't been studied. So there are subpopulations that may have a higher risk too.
Yes.
Hi. Can you tell me how it's determined which diseases that they would practice gene therapy on?
How it's determined? Oh, that's a complicated process. There's no pattern. If somebody has been working on something and has been getting success, like Dr. Medine, and is at a stage where they think it can be developed and used in humans, they would have gone through many different stages to get there, and enough stages, enough experiments in mice and animals and rats and sometimes monkeys or other primates to convince the health authorities like Health Canada that it's safe to try this. That's what had to happen for Fabry disease, for example. And there has to be a need. So although you may be able to put a gene in for certain things, like, I don't know, maybe I can put a gene in to make me a faster runner, but Health Canada might say, well, that's not really that important, how fast you run. You're never going to beat the record anyway. And they will look to see if there's, let's say, a high death rate from a certain disease or it causes severe disability. And then in many cases, we have to remember that there is an industry that then takes a development forward. So a drug company, if you will. Because I might come up with something in my garage, but if it was like something like Google, then that would be great, because you can do that in your garage. Now, if you did gene therapy in your garage, you still need to get past Health Canada before you're going to use it. So some company will have to decide the development is significant enough to make a multi-million-dollar investment in order to run the clinical trials to prove that it works. So there's no formula for this, but those are some of the core components of what happens with one versus the other. Now, the model we're using can be applied to many different diseases. It can be applied to Gaucher disease. And actually, the company that recently acquired the rights to this technology, because we developed it from a government grant, but of course, some company came and said, well, we're going to acquire the rights to this. And, okay, what do? They're a big company, and I'm not. So they're looking at developing it for Gaucher disease as well. And but there's no systematic pattern right now.
What about something like Huntington's disease?
Huntington's disease, right? The genetic mechanism of Huntington's disease works differently, and it's not that easy to treat with gene therapy. Because with Huntington's disease, there's not a spelling mistake. It's a disease that causes dementia and brain loss, and some people can die early from it. But the mechanism, most of what I talk to you about is a spelling mistake in the gene. In Huntington's disease, there's no spelling mistake. It's just that there's many copies of that gene, so many copies it doesn't work, right? Like if you had, I don't know, let me come up with some analogy, laundry, right? So having good, clean underwear is a good thing. But if you had so much that you can never find it in the big mess, it's going to create inefficiency. And in the cell, that does the same thing. The gene gets so big that it doesn't work properly, the cell, and the brain cells will die off. So if we add a copy of a gene in that case, it's not going to help. It already has too many copies of the gene. What we have to do is silence a huge region of that gene. So the approach there is different, and that would be to use a drug to either silence most of the copies, or you may have heard of this CRISPR thing, is to go in there and snip out all the extra pieces so you just have the right amount of pieces left.
So it's like a photocopier that's stuck.
It's stuck. It's just going on and on and on.
Fantastic questions from the group. Any other thoughts? Yes. Whoops. Sorry.
This is fascinating. And you know how some bad people can hack into banks and get all your information?
Yes.
I'm worried about the privacy of information about your own DNA and what that could lead to.
Very good question. Privacy of your own DNA. So some of the things right now, and we're worried about it too, is we don't have it on an electronic database that you can access through the internet. They're still on hard drives. Now, technically, you could still get to it if you broke into the hospital and stole a hard drive, but then you can encrypt the hard drive. But you're right, the vulnerability is never going to go away. However, it's actually easier to hack you than it is to hack that computer. So you could sip some water and leave a little bit of saliva, throw something in the garbage. And if somebody wanted to know what your genetic code was, it's not that hard to get that. That's going to be more hackable than actually the hard drive. Because everywhere you go, you leave bits and pieces of DNA. And all it could be is a coffee cup. That's all we need to sequence it. But so certain safeguards will have to be built into those databases. I mean, we hear about hacking all the time. I was speaking to somebody who does security for one of the big banks. And they said, when's the last time you heard a big Canadian bank hacked into? I'm like, well, I don't know. I suppose it can happen. He's like, yeah, but it's my job to prevent it. And if you think about it, most of the security lapses were because they're kind of like plane crashes in some way, right? Certain steps were not followed. Somebody put in a wrong part. Somebody miscalculated the amount of fuel. Somebody did a shortcut somewhere. And there was a security breach. But the folks that invest a lot of effort into it, things tend to be a little bit better. But yes, there's never a zero risk.
On your slide that showed the predispositions of Ashkenazi Jews to have various diseases, there was about 5 of them. Could you just give a quick rundown of the characteristics of each of those diseases?
We okay with that? Oh, my slide is somehow still up. Parts. My whole computer stuff is up there. So you could take a picture of it and figure out what's on it. Okay, so Gaucher disease. Gaucher disease is what we call a storage disease. And what happens is there's different molecules our bodies make. And they have to recycle them. And if they don't, they build up. With Gaucher disease, they build up in the liver and produce a big liver. They build up in the spleen and cause a big spleen. They cause problems in the bone. And the most severe type of Gaucher disease, it's actually called type 2. You don't live past a year. There's another type called type 3, which starts affecting the brain and can cause neurologic delays. The most common type, the one that has this carrier rate in Ashkenazi Jews, does not have the brain affected, but the rest of the body is. And it's treatable with a number of different therapies that go and fix the recycling component or make sure that less stuff is being made and fix the storage component. Cystic fibrosis. Your lungs don't work properly. You don't digest things properly, digest foods properly. You don't gain weight. You don't sweat. And you develop very severe lung disease. And like I said, in the older days, many people die before their teens because the lung disease is so severe. They used to have iron lungs that used to breathe for them, kind of like for polio. Tay-Sachs disease affects the brain mostly. It causes the brain to start decaying. The kids have seizures, and the kids will die, often before 1 year of age, from severe seizures. Familial dysautonomia. Your peripheral nerves are not working. You can't stand up. You can't touch yourself. You just lie there like a floppy pile of flesh. You have to have a machine to breathe for you because you can't generate enough force to breathe. Spinal muscular atrophy. You also can't move. You have to have a machine breathe for you because you don't have any function of your muscles or your nerves. There's other bad stories like that. So there were more than 140 diseases on that list, all kind of with bad stories like that.
So Dr. Kahn, you alluded in your talk that the community in Toronto may be a bit better organized in terms of screening and allowing young parents who want to be tested. It's a bit easier for them to do so in Toronto than here. Do you want to elaborate on that and suggest what's needed?
Doing the testing here is just as easy. It's a blood test. It's just that we haven't organized it. So events like this, where we get to interact with the community, bring this issue forward, and then if the community feedback is this is a program they want to have, then we take it to the powers that be and we say, hey, this is coming from grassroots community and they would like something like this to make it happen. If we saw an individual couple, that's not an issue. We can do it. So the technology is there, the ability is there. It's just if the community wants to channel more referrals in, then that can certainly be something that we talk about. Yeah.
I was going to say that I remember in the 80s in Houston, the Rabbinical Association made a point of insisting that all couples that came to get married were screened for Tay-Sachs. So it wasn't at the time, well, we're going to decide to have children, but it was actually a factor in terms of knowing right at the start that they might potentially produce a child that had Tay-Sachs. Of course, interestingly as well, though, from an ultra-Orthodox part of the community was against testing for Tay-Sachs, because the reason that people tested for Tay-Sachs was they then had the choice of whether to abort the fetus.
Right, you bring up a very good point, that if we go back, let's say more than 10 years, and you and your partner are carriers for Tay-Sachs, nothing could be done before the pregnancy happened. The pregnancy would happen, and then you would test to see if the pregnancy is affected with Tay-Sachs, and the only choice was whether to terminate the pregnancy. Today, what's possible is you kind of do a test tube fertilization, and you have an embryo that's about 8 or 12 cells. You take one cell out, you test it to see if that embryo inherited the 2 copies of the gene. And you then put the colony in that's not affected into the mother to carry on with the pregnancy. It's called pre-implantation diagnosis. It's not covered on the public purse. It takes 2 rounds, average $10,000 to $20,000. So it's not for everybody. But it can, what happens there is then you can test for it prenatally. It's more than 90% effective mathematically. But that reduces the need to have that abortion. It brings up the other need about the issue about the embryos, and you can carry that forward many times, but no perfect solution so far.
Could you please talk about gene therapy with Tay-Sachs disease, or is it the therapy that you've just mentioned
Sure.
Related to Tay-Sachs?
So the one we used for Fabry disease, where we inserted a gene into stem cells that we harvested, and a stem cell is basically a cell that will set up a population, just going to get a drink of water, where it can make copies of itself. So you start off with one cell, it makes one protein, and it can turn into 1 million cells and make 1 million copies of the protein, enough to make a difference. So we did that in Fabry disease, but Tay-Sachs is a brain disease. That approach is not going to work in the brain. For brain disease, you'd have to inject that gene into the brain somehow, which people have done. It just doesn't work that effectively because the brain is not a stem cell. And you have to get that gene in enough copies of brain cells with your first blast that it's going to be effective. So that brings up some additional challenges on how that's going to take place. Usually in those circumstances, what might work better is a drug that can get into the brain and modify how that gene works. So people are using different approaches, but in that approach, I don't know that a gene therapy approach might work that well. And the gene therapy has been tried in a disease that looks like Tay-Sachs. Is called Batten's disease, or neuronal serolipofuscinosis, just showing off these long names. But anyhow, and I had a patient that went to a place in the United States to get 8 injections in the brain of the gene. It didn't work because it may have been a little too late in her, but just the physiology of that was more complicated.
What about Niemann-Pick disease that starts in the late teens? Niemann-Pick
disease. Well, you guys are a very sophisticated audience. Okay, Niemann-Pick disease, big names. Niemann-Pick C, there's 3 types, A, B, and C, and they all have a neurologic component, and they all can produce a big liver and spleen, and in many ways look like Gaucher disease. So the problem is the fact that the brain deteriorates. And there is a small molecule compound which, if it got into the brain, might help. So there's not a lot of ways to get into the brain, but one way is you stick a needle in the back into the spine, and you inject the drug directly into the spinal fluid, and then lie them with the head down so it goes down into the brain. So that is a treatment that I use, actually. We did 2 people on Wednesday. I got another girl coming in next week to do it. So we do that treatment right now 6 times a month in different patients. And they get it every 2 weeks. We put a needle in and inject the drug in directly. So it's one way to try and treat it. And those patients, they say that it really helped improve their walking. And one of them, she hasn't developed a seizure, and frankly, she shouldn't be alive, so it must be doing something. So I'm thinking we need to find a compound like that for Tay-Sachs, that it might not be gene therapy. But I'm not the investigator of the trial, and maybe the investigator of the trial would say, you don't know what you're talking about, this stuff is really going to work, which would be great if it did.
Is that treatment covered with Alberta Healthcare?
No. All the gene therapies are experimental, basically, certainly in Canada. But in Europe, there are a couple of treatments that would be, that the public system would look after. Because they started doing it earlier than us, and they've done it in some very nasty diseases where there was no choice but to do it to save the child.
I think we'll have time for one final question.
Just a comment. Calgary did have a Tay-Sachs clinic set up about somewhere between 35 and 40 years ago, and they did do a screening, but there hasn't been anything since.
Okay, that predates me by quite a bit. So, and it's good to know, because when I came here, I've been here for about 11 years, and I did most of my training in Toronto. And I mean, I know I'm coming to a smaller place, and they may not have it, but it was such a simple thing. I was like, how come we don't have this? Because people were using it in Toronto. We'd see the results come all the time.
Just wondering, we had talked about these ancestry DNA and other things that you see on TV. Are there any risks in doing that? Is it just sort of curiosity and entertainment? What's the value of doing some of that? Or risks?
So we're talking about places where you can find out, I don't know, if you're 20% Scandinavian and 40% Italian and so on and so forth. And so they're basically entertainment right now, because in order to give a diagnosis, you have to have a license to give a diagnosis. And in Canada, the regulations won't permit them to tell you that you're at risk for Alzheimer's, or that you have Tay-Sachs, for example. So in the United States, where one company, 23andMe, for example, is doing that kind of stuff. Actually, they have been licensed by the FDA to provide an answer for 5 diseases. The only thing is, in Canada, I mean, if you look at technology, usually we kind of wait for somebody else to come up with it, and then we're like, yeah, we'll do it like that, and we'll have 10 more rules. So we're waiting for that part to get added on to this. But when that part comes, and it's inevitable it's going to come, that some company will be able to say, you're a Tay-Sachs carrier. Now go find somebody to talk to about it. But, or some other disease. But they haven't gone into that yet. But it's not hard to do. They probably know that risk in many of the people that have been sequenced. But right now, it's mostly for entertainment, because if you go back in our genes, all of us kind of originate in Africa at some point. So even if you find out you're 80% or Italian or 30% Spanish, eventually that gene will trickle down back to Africa somewhere. So how that affects health, I don't know. So it's kind of neat and interesting. It's not that it doesn't have value. I mean, it's very important for people to know those things. And so it is serving a purpose. And they're not that inaccurate either. They're actually pretty good. They're using fairly good science to do it. I mean, if you look at the concept of an egg, so an egg has genetic information in it, and it has these things called mitochondria. How many people have heard of mitochondria? Man, you guys know so much about this. Okay, mitochondria have their own genes. And you only get your mitochondria from your mother. The only thing you get from your dad is the nuclear genes that come in through the sperm. So you could trace the mitochondria back to find out kind of where your ancestors were 100,000 years ago. In fact, some would say you can even trace it back to find Eve, or an ancestral Eve if you went back far enough. If you do that, you find out it actually all leads back to Africa. So that's kind of where, as humans, the early beginnings likely took place, if you're a geneticist. And so the ancestry stuff adds some more flavors to that. If you look at the Ashkenazi Jewish population, if you kind of did that with them, you would say a huge portion look like they're of Italian ancestry, and a migration took place at the time of the Roman Empire, and then as the migration took place, then many adopted Judaism and established communities. That's kind of what it tells us about the Ashkenazi Jewish population. So you get a lot of information digging up those things that somehow would trickle into something that's health-related.
Well, I think we now understand why many Jewish people like Italian food. But on that note, and yeah, that's the other one. So I think we are so lucky to have had the opportunity to hear from Dr. Khan this evening. It's been a fascinating journey into the world of genetics and science, and really lucky to have his insight and perspective and allow us to see not only what the future holds, but what amazing things are happening today. So we have some snacks for you out there and some great food, so please join us. But first of all, join me in thanking Dr. Khan for a great presentation.
Thank you.
And just a quick housekeeping note, if you're someone to want to do a calendar hold or hold the date, our next Tzed talk is scheduled for May 26th, actually, and we'll be bringing in Dr. Daniel Kollick, who is a disaster medicine specialist in Ontario, but has done lots of work in Israel, and will be able to speak to how you and Israel prepares for various kinds of disasters. Big thank you to everybody for coming. Have a great evening.